We have other optional libraries, but this is popular one. Okay. The distribution that you download installed, it comes with this MDK. But you have to download this MDK dataset separately. If you don't download this, right, some of the code that we have here, you can run it without any issue. The rest, they will not be able to run properly. Okay. So download this, check to see whether it is done or not. If yes, close it. Okay. So we move on to the next step. Text data. We use a simple one with only 3 sentences. Okay. So this data is noisy because it has a lot of information that we actually can extract from here. And there are things that we think that they are not so important. For example, punctuation, numbers, and so on. So normally we want to remove punctuation. So what are punctuation? What is considered as punctuation? What is considered as not? And what kind of punctuation you want to remove? You can actually refer to this string module. In the string module, there are a number of constants defined. For example, we have ASCII lowercase, uppercase, we have digits, and so on. But we would like to use this one, punctuation. Okay? So you can get the list of punctuation from here. Either you use this directly, whenever you see any punctuation, right, you remove it. Okay? So this can be the standard. Alternatively, you can download this and you can remove some. There are researchers who did some study and they found that punctuation actually is useful. For example, exclamation mark, question mark, and a few more. They carry slightly more important information than the others. So if you remove them, right, it will result in model perform slightly worse. So there are times it is important for us to keep some punctuation rather than removing more. So for this study, we will remove all of them. We have learned how to use this, right? Last week, reject regular expression. This is one function defined under the RE module. You can use this substitute function to search through a text, and then you will find matches for this pattern. If there's any match, it will replace the match with the empty string. So this is the pattern. If there's anything matched with any of the punctuation, then it will be removed by replacing it with empty string. So we remove the punctuation. So this is only the first step. We use the original text as the input, then we do some cleaning, and then we get this clean text. The clean text will become the input for the next step. So what should we do next step? We want to remove numbers. Okay, numbers are important. So for example, your salary is 20k, my salary is only 2k. So we can see a difference, right? So number is important. But if we consider numbers, right, it will actually increase the complexity of the computation. For example, if we only consider from 0 to 1 million, so we will have 1 million possibilities, right? 1 is different from 2, 2 is different from 1000, and so on and so on. What if we have a few numbers, different combinations? Then the complexity will be increased. So we want machine to understand the meaning, but we want to simplify it. So machine can understand the meaning, but not like how we do. For example, if we remove 2, right, and 4, we can somehow reduce the complexity of the computation. Even though machine cannot understand this like how we do, machine can understand that this is about buying vegetables, tomatoes, and cucumbers. But how many to know? Okay, next. So we can do this by using this pattern. So it will remove all the numbers. Okay. So why you put an R here? Okay, we check. So can you copy this one? Add a new cell, put it here. Then you remove the R. See whether you can see anything. For some PCs, when you print this, right, you can see a symbol here. Others, right, you don't see anything, but you can see that something is printed here. Just that you cannot see. Okay. So the backspace is combined with this backslash, right? Backslash is combined with this V. It has a special meaning. But unfortunately, when we do reject, we write the pattern, right? We also use this. So you can check reject, special, sequence. We have this. Okay. Special sequence. This is the special meaning, backspace. But when you use this to do reject regular expression, this one has a different meaning. It matches the start and the end of the string. Okay. So if you do not put an R in front of it, right, when you print this is what you see, something is printed, but you cannot see it. But when you put an R in front of it, right, the special meaning is removed. Because now, this is a raw character. This is a raw character. Everything is raw. Okay. So make it a habit to put an R in front of the pattern. Okay. Put an R. You don't have to put this in front of the string, but put it in front of the pattern. Okay, next, lowercase conversion. Why is it important for us to do this? When you read some papers where they talk about doing NLP or supervised machine learning, the use of text, they normally will consider lowercase conversion. It is not a must, but normally they will do it. Why? So we look at this one. We have vegetarian, right? We have restaurant. So to us, this word alone and this word alone, they carry the same meaning, right? But machine cannot understand that these two carry the same meaning. Okay? So it is possible that machine see this as something else, machine see this as something else. This is this one symbol, this is another symbol. So to make this thing to be processed in the right way, we want to do lowercase conversion. This is a form of text normalization. Okay? We standardize it. So now we have done some string processing, very commonly used steps. So this is what we have. We remove numbers, we remove punctuation, and we do the overfitting. Then next we do word organization. Okay, word organization, we want to divide sentence or text into tokens. And for word organization, we make a token as a word. So it is possible that we can have a token as a character or a sentence, but normally we will make it a word. So let us start doing this onto the original text. So you can see that when we do it onto the original text, we can do it in many different ways. We can use a split function. We can use this word tokenize defined under LDK. We can also use some other functions. So these are many different ways that we can use to do it. Okay. Now I want you to compare the output. For the first one, with the use of split, this is the output. By right, we should get the same output, right? Because this is just about tokenization. But you see, this output and the first one is different. This one and the second one is different. This one and the third one is different, and so on. So they are all different from each other. We don't want, because of this, it will affect the result. So what can we do? Let us try to apply this onto the clean text. We do the same thing again, but we change the text. Okay, we change it to clean text. So when you try the same function again, you can see that it will give you the same output. So in other words, when you want to do tokenization, never ever do it as a first step. At least you make sure that you do some cleaning, important ones, like for example, number removal, maybe punctuation removal, and lowercase conversion, then you do it. Otherwise, the result will be different whenever you do it again and again. It is also possible to do sentence tokenization, just that we have to consider a sentence as a token. For example, one sentence, this one is another one, and this is another one. Okay. So we will skip this. Okay, next, stop words removal. Okay, what are stop words? Why you want to remove stop words? Stop words are words that have very little semantic value. So it means that they contribute very little to the entire meaning of the sentence. For example, in this sentence, we have the word some, we have the word and, we have the word from, the. All these are stop words. They contribute to the meaning of the sentence, but just very little. If you remove the word some, you read the sentence again, right? You still can understand the meaning. Just that it is changed a bit, just a bit only. If you remove and, right, you still can understand it. If you remove the word from, the, and so on, you still can understand it. But if you remove too much, right, then maybe we can have some difficulty to understand it. But after all, the way for machine to understand the meaning of the text is different from how we do. So we want to keep important words. Okay? So we normally will remove stop words, normally, but not a must. We can have stop words in many different languages. So we check out, this one is in Arabic. Okay, these are all stop words. And then we have those in English. Okay? So you are supposed to remove stop words from the plain text. So you can do this later. You can use the list comprehension to do it. But when you do stop word removal, you have to be very careful. There are also some researchers they have done some study. They prove that stop words are actually important. Okay? Even though in most cases, after you remove stop words, right, machine can process it well. But now look at the way we convert text into vectors. It is different. It takes into consideration context. So stop words should be important. Okay? For example, okay, let's say after watching the new movie, Superman, let's say you don't like it, you leave a review on the website, and we want to process this so that the machine can understand it. If you do stop word removal, you can check out, is it a stop word? Yes. Do, is it a stop word? Yes. not. Is it a stop word? Yes. So you will remove this tree and the as well, leaving only like movie. So the meaning is reversed, 100%. So if you do stop word removal, be careful, especially when you are going to deal with sentences that contain words like this, negation words, that can reverse the meaning of the sentence. Okay? And so you will do this later as exercise 7. We have one output here with all the stop word removed, which is this one. Here. Okay? But you can check this one, check the answer of yours and this one, see whether they are the same or not. Okay? The next step is about stemming and lemmatization. You can do either one. When you do stemming or lemmatization, the main purpose is to reduce words to the base form. For example, we have the word change. This is the base word or the root word. Then you can modify the word and you can use it in different situations. For example, you can change to changing, and then changes, change, or just use change. So to us, these four, they carry similar meanings, right? Almost the same. But machine may think that these four are different from each other. So why machine is so stupid? Okay, just ask yourself. If you look at these symbols, can you differentiate them? Cannot, right? So it's the same to machine. Machine cannot understand the language like how we do. So when machine see these two, they look very similar, but they are not the same. So machine doesn't know whether they are the same or not. So to prevent machine misinterpret the meaning of the words, we also want to do this. We reduce all of this to the base word. So when you reduce them to the base word, right, they carry the same meaning. But of course, when we do the reduction, right, we have to be very careful. Change and changer, they are not the same. So if we accidentally remove the R, we make change and changer the same, right, then the meaning is change. Okay? But if you use stemming, right, you can also achieve the same effect. Just that there's a risk. There are times words can be reduced to invalid words. So lemmatization and stemming. This one is done based on the rules of the language. This is more complex. This one is done based on the heuristics designed by human. But the language itself is too complex, so the heuristic is not complex enough to cover all cases, all possibilities. So human may overlook something like this. Okay? So there are a few different Lancaster samples that we can use. Lancaster sample is one. So it is available in LBK. So you can reduce all these words to connect. Then for drive, it accidentally remove E and become invalid word. If you think that Lancaster stammer is bad, never mind, you can use other stammers. We have Porter stammer, we have Snowball stammer, and some other stammers. Okay. But if you don't want to have the risk, because we don't know, there are times Snowball stammer may make the mistake, then you can use lemmatization. But there is a problem with the use of lemmatization as well. If you run this, you will notice something is not right here. Can you check the input and output? What is not right here? Almost no change. If we, based on our understanding, maybe connect and connecting carry very similar meaning, right? But the thing is that, you see, connecting. So this is the issue. When you use lemmatization, the chances to have words to be reduced is relatively lower compared to stemming. Stemming is very aggressive. Okay? So if you want to play safe, then consider lemmatization. And now we do this onto the plain text, and you can see that the reduction is very minimum. It only change vegetables to vegetable, plural to singular, only 3 or 4. Okay, so very minimum. And next we have this part of speech tagging. We don't have to do this unless for some of the operations they require the presence of the tag, part of speech tag, before they can do something. For example, I like to read books. If let's say you do not know all these words, they are like different symbols. It is possible that you may misinterpret one of the symbols. If let's say this symbol can carry more than one meaning. In fact, the word here, books, it is a polysemy word. Polysemy word means that it can carry more than one meaning. So we can use book as a verb, we use it as a noun. So if let's say you ask machine that cannot understand English language, cannot understand all these words, the machine look at this one, these are all different symbols. Machine may think that this is a book. So when you put a label here or a tag in here, you know that machine will know, oh, the row of this word is a noun. The row of this word is a verb in this sentence. So machine can do the interpretation more correctly. Okay. So everything is available in LTK. Okay. So these are different tags. Okay. And then you will do this one. So you can see it will be generated for you. Okay, now we do it onto the plain text and the original text. And you can see the difference. Plain text comes first, followed by original text. So we do part of speech tagging, and it works. Okay, both also have the result printed. But if you look at this output, pick in the original text, we have pick up. So this is supposed to be verb, right? But because too much information is removed from the sentence, punctuation, maybe numbers and the rest and stops, right? So the machine cannot actually do this tagging very well. So it mistakenly label this as a noun, but this is a verb. So if you check here, pick, this one, verb. So if you really want to do part of speech tagging, you do this as a first step. Then you keep all these labels, the noun, the verb, and so on, then later you use it. Okay? Don't do this last, so you see this is not going to happen. Okay, chunking. There are types of, after you've done tokenization, right, there are a few words that should be combined to form something else. For example, the name of a person. We have James, we have Smith. So this chunking can actually tell you which two words or three words, right, they actually refer to certain entities. Okay? You can actually print the tree as well. You can also do this manually. We have compound term extraction. You can use this multi-word expression tokenizer and manually combine them with the use of underscore, like this. Just in case, tokenization, right, divide this into two different tokens. So you can combine it. When you have done this already, right, this will become one token only. But you have to be careful because this is also punctuation symbol, right? So if you do punctuation later, right, punctuation removal, this will be removed. So be careful with the sequence. Okay, so we take a 5 minutes break, then later we'll continue with NumPy, data frame, and finally one example usage of the things that we have learned to see how machine actually can do comparison between the meaning of the text.
Peace. It lies.那这种，那这种应该就能出。我的意思，不一定。找一个在一起。你从上面开始 enter 下来。Import string. Oh.
这
就没问题了。我有一个学生，我现在可以去。谁我怕这种字超不了。很遗憾的就是他也成功吓死我了。是丢这里，没在丢。15，超了整个半价了，这所以有一点点。
Okay, so we continue with NumPy. Okay, when you want to import NumPy, most probably you want to deal with arrays. Python does not have built-in arrays. In order to use array, you can either import this library or some other library. Okay? This is not the only one that allows you to do with arrays. Okay, so we can create array. So when you create the array, right, you can see that there's a label here. This is an array. So that you can tell array is different from a list. Okay? So we can check the type. Multi-dimensional array. Okay, it is important for us to check the shape. So when you see only one number, comma, one number array, so it means that this is 1D array. For 2D array, right, you can see two numbers. So let us create 2D array. Two numbers. We don't usually deal with arrays because it is not so flexible. You can only put numbers or something that is of the same type. Okay? So we will create array. Maybe as an intermediate output, and then we convert it to something else. And now we just quickly skip this one, just to show you we can create 2D array, 3D array, and do something. Okay, we have created 2D array. Later we will convert this 2D array to something else. Okay. So next, this is the one that we will be using, data frame. So in order to use data frame, you will have to import pandas. Okay. So what is data frame? It is more than 2D array. It is a 2D array with heterogeneous data. It has a mix of numbers, boolean values, and any other data type. Okay? And it has labels for the columns and labels for the row. So it is easy for us to understand the data. Okay, for example, given this array, we can convert it to data frames. We need to import this one first. So now this array looks like this. Every row has a label. Every column has a label. Okay? So initially, we only have this one initially. So if let's say you do not provide the label, then it will give this index numbers to you as a label. So you start from 0, 0. You can check the shape. So the shape here, 6, 4, it doesn't include this, for example here. 6 rows, 1, 2, 3, 4, 5, 6, right? It doesn't include this one. 4 columns, 1, 2, 3, 4. It doesn't include this one. Okay? So you can check the labels of columns. For something like this, right, maybe you think that this is not important. But if let's say you are going to read a very huge data with many columns into the data frame format, right, you may want to first check what are the labels. What are the labels for the columns? Then you know whether there's any useful information or not. It will tell you what are all the headers or the labels. You can also print the labels of the rows. You can also replace the headers or the labels with some other values. Let's say you want to check movie reviews and you use 3 or 4 different movie data sets. Maybe the labels that come in the data is not consistent. So there's one column that tell you what is the classes maybe good or bad, positive, negative. But the label may be different from the others. So you can standardize it, change the label. A cookie review, we have this file, right? With 4 cookie reviews. So this is a simple one. It only has 3 columns: user ID, the rating value, and the reviews. In total, we have I think around 912 reviews. Labels for the columns are also provided. So you can read this into the data frame. Okay. Then you can see now, this is the label for the column, label for the column, label for the column. Every row also has a label. If you do not provide the label, right, then this will be the label provided to you. Normally, if you want to check the first few records, the last few records, or maybe more records, okay, you can put here numbers. Let's say if you want to see only the first 5, then 8 by default only see the first 5. But if you put a number here, 10, then you can see first 10 or first 20. So it is good for you to check some records. For example, if you do not check the records, right, you will not know if some of the reviews are written in this level, right? So it is good for you to check. Okay. Then this is the same thing. We print all the labels. Okay. If you do this, the data frame has a name. VF dot column name. The label of the column. You will print the entire column. Okay. This is the first column. This is one way for you to print the entire column. This is another way. Reviews. All the reviews. But because the review is too long, you cannot read all of them. Okay. When you use list, if you want to change the elements value, right, you have to use loop through the list, right? But when you use data frame, you don't have to use loop. For example, for this column, the entire column, I want to change all the reviews to title case. Okay? This is sentence case. I want to change them to title case. When you run this is output. Title case. Every word has the first letter changed to uppercase letter. One line only. Okay? But when you do this, right, this is only applied onto the copy, not the original one. You have to do this. You assign the change to the original one, then yes, the change is done. And there are times you may want to access not the entire column. You may want to access only one row, one column, maybe one cell, one event value, or maybe intersection of rows and columns. So you may want to use ILOC or LOC. For ILOC, this is integer-based location. Integer-based means you're going to use index value, indexing, okay? Index position. For example, if you want to extract the first row, what is the index value for the first row? 0, right? So ILOC, you put 0 here, it will give you the first row only. So if you change this to 1, right, then the second row. Okay? If you want to access the last row, you can use -1. Okay? You can also use this. What is the index value for the last row? 912, right? Index value for 912, last one is 912. Same. But we use index value 1. Then, if you want to extract the data in a different way, I want all rows from the first column. Then you have a comma separate these two parts. The first part before the comma, this is meant for row. The part, second part after the comma is meant for column. So if you do not write the starting and ending number, this is slicing, right? It means all row. Okay, all rows. Then this one, index value 1. 0 means the first column. All rows from the first column. The IDs. Then all rows from the last column. Last column is review, right? So review all the reviews. And if you put here only one row, one column, it means intersection of the first row and the second column. Second column is correct, staff, the rating. So 5. You can also use this to do intersection of multiple rows and multiple columns. So we do this because we want to check some values after maybe we do pre-processing or before we do pre-processing. So it is important for you to know whether it is successful or not. It is possible that you write the code, right? You want to remove something, you think it works, you do it. But because you didn't check out, nothing happened. So it is good to check out. Do something, check output. Do something, check output again. Okay. So we can also use LOC. LOC is similar to ILOC, but we do not do this with the use of indexing. We use label. Label. Okay, we use crop first. Crop. Okay, you look at this one. All columns has one label, right? The first column, the label is this one, user ID. The second column, the label is staff. Third one, review. And coincidentally, the label for every row is a number. It starts from 0. So it looks like index number, but this is the label for the row. The label for the row, first row is 0. The label for the second row is 1. So when you do this with the use of LOC, right, it seems that if you are doing this with the use of indexing, but called infinity, this is 0. So when you want to extract the last row, right, can you do this? Minus 1 is indexing, right? This will not work anymore. Okay. Because this is not the label one. So the last row, you can use this formula. The size, in total we have 913. Minus 1, because it starts from 0, right? 912. Either you do it like this, or you can just put 912. 912 is also the label of the last row. 912. Okay. Then the rest, they are all the same. All rows under this user ID column. All rows under the reduced column. The intersection of the first row and the stars column. Okay. The intersection of multiple rows, 3 rows and the 2 columns. Yeah. So there are some exercises, you can try to do this later. Now we move on, and we do this. Text block. Okay, other than NLTK, we can also use text block. So we try to do this. Okay, text block doesn't come with distribution. So when you run this, right, you can see that it says no module name text block. This is normal. So you can do the check-in from here as well. Click on the search icon, then type Anaconda. Then choose Anaconda Pro. Okay. Click on the search icon, type Anaconda, and choose Anaconda Pro. So it looks like one prompt. Then when you use this, right, you are going to interact with Conda. So we start with Conda. This is command Conda. What do you want to do? You want Conda to list down all of the libraries. So Conda list. And you press enter, right, it will list down all the libraries. So you can check out, scroll up and down. But one fastest way is that you can type Conda list and let's say text block. It is not there, right? So we check to see whether it's there or not. So when you check to see whether one library or one module is there or not, if you don't see the version number and also the name, it means it is not available. If you can try with this last one, ZSED. Okay? Conda list ZSED. If it is there, then it looks like this. With the version and with the name. Okay, so to install this one, you can use this command. Pip install text block. Okay, press enter. It won't take long because the size is very small. Okay, done. And now we run this again, it works. So we can use text block to do tokenization. We can use text block to do spelling check. We can use text block to do part of page tagging. Okay. We can also do this translation. In the past, it worked. Text block make use of Google Translation. Okay, but now it doesn't work anymore. So you can try. You can do this. Install another library, and you run this. It will work. Okay, we use Google Trans. Okay. So here, experiment this later. Okay, we come to the last part. Count vectorizer. Later we will be using data frame. So what is this count vectorizer? We use it because it is the implementation of one approach called back of words. Okay? We use the back of words approach because we want machine to be able to understand the meaning of the text. For example, if let's say we have one document, it contains all these words, right? You actually can identify what are the unique words you can get from here and how many times they appear in this sentence. So you actually can convert this into this format, and this is actually known as back of words. Okay. So we use this to help machine to understand the meaning of the document. Okay, let's say we have another document where the use of the numbers, the words like eater, either, maybe they are comparable, then maybe they are highly similar. Okay. It doesn't really look into the meaning of the document. Okay, let's try it. It's based on word count. Let's say we have this sentence. The lecture is in noon, please come to the lecture on time. Machine cannot understand this one. So we do tokenization, we split it into tokens. Machine still cannot understand the tokens. So machine has to assign one index number to each. So So we have 0, 1, 2, 3. So when we refer to null, machine will see 4. When we refer to please, machine will see 6. Then machine will actually try to understand the whole meaning by checking how many times they appear in the sentence or the text or document. So this is how we do it. Let's say we use this one or original text. We use this count vectorizer to create the count vectorizer object. So if you put here stopwords equal to English, right? It means that you want to remove stopwords. So the list here is shorter. Let's say we remove this and you can see that the output is longer because the stopwords are there. But if you want to remove stopwords, then you put it here. Okay. So we create the CV object, count vectorizer object, and then we fit this object in the text using fit and transform function. So two things happen here. Fitting happens to do this. Split the sentence into tokens and assign one index value to it. So fitting will result in creating the vocabulary. Okay. Then transformer will check the frequency, the count, how many words are there and how many times they appear, and give you the vector. When we can convert text into numbers, we refer to this as vector, then the machine actually can understand the meaning. Whether this one is similar to the other one or not. Not really understand it, but somehow can process it. Okay? Because machine can deal with numbers. So, okay. We cannot understand this, right? Because machine cannot understand words. Machine will assign one number to every single word. So machine can understand what is 5, we cannot understand it. Until we print it out, for example, 5 refers to hi, 6 refers to Mr. So this is how machine can understand the word. Okay? Because machine cannot process word text directly. So when we have vector generated, right, we can measure whether two documents are similar by measuring the cosine similarity. How far they are, how close they are. Okay? So now let us do one simple experiment. We scroll down, and we look for this one. There are 5 sentences here. So if let's say we want machine to try to find which two sentences are most similar to each other using backwards. Okay, how is it? So how? First thing first, we have to understand which two are most similar. The first one talks about weather, right? The second one talks about dream. The third one talks about encoding technique. The fourth one talks about a different dream. And then the last one talks about sales. So this is weather, dream, encoding technique, dream, and sales. So it seems like number 2 and number 4, maybe they are more similar to each other, right? Okay. So let us do this. We pass the 5 to the machine, then machine will try to convert the text into a vector. Okay? One vector for each. So we use count vectorizer, we do this, blah blah blah, and then the vector. Okay? The next, later you can go through this and understand this. These are just steps to try to do pairwise combination. So we use cosine similarity to find how different it is between 0 and 1, 0 and 2, 0 and 3, 0 and 4. So this 0 refers to, yeah, correct. We have 5 sentences, right? 1, 2, 3, 4, 5. So machine will understand the first one as 0. So we pair them like this: 0, 1, 0, 2, 0, 3, 0, 4. 1, 2, 1, 3, 1, 4. So we do pairwise combination and we check the score. So you can see that the machine thinks that this one and this one, they are most similar to each other. The score is highest, 0.4. But this is wrong, right? So let us try the other one. We use TF-IDF. Here we scroll down, we have TF-IDF. Term frequency inverse document frequency. We do this one first, later we try to understand how it works. We scroll down and look for one. The last part here. We just change count vectorizer to TF-IDF vectorizer. We change count vectorizer to TF-IDF vectorizer. Okay? So when you run this, right, you can see that we have a different way to do this conversion. Convert text to vectors. Now we no longer see 1, 1, 1, 1, 1, 2, 2, 2 in integers, right? We see real numbers. Okay? Then we do the same thing. We measure cosine similarity, and you can see that now number 2 and number 4, they are the most similar. Even though the score is quite low, 0.23, but they are the most similar among all the pairs here. Okay. Let us try to understand why TF-IDF works in a better way. There are times back-and-forth approach can work better, but by right, TF IDF should go better by right. Okay. Why? Let us understand how it works now. Okay. Assuming that we have 4 documents here, 1, 2, 3, 4, and each document only has 1 sentence. So if we remove small words, it will result in every document has lesser words. These are important words because we remove small words, right? When we use this characterizer, this is what you see based on counting. In D1, there's 1 name. In D1, there's 1 number, so 1, 1. The rest, they are all 0, right? So this is how it goes. But when we use TF-IDF, we have a different type of number, right? All are real numbers. So this is calculated using the formula given. Okay, why D1 we have 0.3 assigned to name, 0.3 assigned to number? Why these two so high? Even though they look like very low, but 0.3 is very high, the highest. 0.03 is the lowest. So D3 has 0.03 assigned to car and Hyundai. Why these two they are lowest? Why these two highest? Okay, we go back here. Okay, why D3 has car and Hyundai? These two they are assigned the lowest score. Why these two they are assigned the highest score? If you are asked to use the word car and the word Hyundai, these two words are to differentiate D2 from D3 from D4, can you do it? Cannot, because all of them contain car and Hyundai, right? But if you are asked to use name and number to differentiate D1 from the rest, you can do it. Because this is actually very special. It is only used in D1. Just imagine now, if D1 is about cooking, it's a magazine, talks about cooking. You have many different recipes. D2, D3, D4, they are like sports magazine. They have badminton, they have football and so on. Do you think it is possible for you to find olive oil, cabbage in D2, D3, D4? No, ma. That is impossible. That is why important words that appear only in one document, right? In the maybe few documents, they are used to uniquely define the meaning of the document. So that's why name and number, these two are assigned higher score. Unlike this one, if you use a characterizer, see, NAFTA 1, name also 1, car and Hyundai also 1, 1, 1, 1, 1. They are equally important. If let's say we have car used 2 times, right? Then car is even more important, right? So from here you can see how these two works, and this is why this is better because it takes into consideration the importance of special words or relevant words. It also reduces the importance of stop words. If you assume car and Hyundai, these two are stop words. Why? Because they are commonly used in many documents. Any words, when they are commonly used in many documents, right, they carry very little special meaning because they are widely used. Not important. Okay, so that's all for this. Please go through this. Next week we will be doing supervised learning, and most probably we will be doing a little bit of NLP. Then only we do model training. Okay. So if you have any questions, let me know.